Yeah, I'm Fabio. Hello, everyone. Um, I hear myself, it's so weird. Okay, so today I'll be presenting to you a bit of how to optimize um, code performance with time complexities and space complexities, and doing some analysis to that. In the end of this talk, I hope that you know everything you need to know about this topic. I know that it's very important, mainly for backend. I don't know if graphic design is so important to have time complexity, but this is very important for our day-to-day basis. So I hope that you understand with this talk. So we have this somewhat of index, this agenda. First, we'll talk about how some definitions and measurements, so we are on the same page about that. Then we will talk about STEM complexity, and then some truncation and asymptotic complexity, other concepts. We will compare some notations and go to space complexity. We have some techniques of calculation for mainly for space complexity, and we end on sorting algorithms. In the end, we have a final exam, so be ready. um, yeah, I think this is already what you already know by our colleague. But yeah, I have 4 years plus of experience in software engineering. I worked in backend, front end, web development, and I did some freelancing job as graphic designer when I was even younger. I have a master's degree, bachelor's degree, as already said, and I'm a huge gamer, and I do some collecting on the side. Okay, yeah, some definitions that we need to know about. What's an algorithm? Oh, okay, I know that this is really basic, but generally speaking, an algorithm is just a process or set of rules that are to be followed in calculations or other problem-solving operations, especially by computers. This is the default definition of algorithm. More technically, it's a finite set of statements that, when executed, guarantees a correct solution in a finite amount of time. Finite is the buzzword here and most important that we will see. What distinguishes a good algorithm than a bad algorithm when they try to do the same solution or fix the same issue? It's mainly the one will run in less time or consume less memory, or and. But depending on the case, one is more important than the other. Efficiency measure, we have the efficiency of an algorithm ends up being measured by the number of resources consumed by in solving an algorithm of the size n, then being the length of our input. The resource that we're most interested at this time is time. The same techniques can be used to analyze other consumption of other resources, such in memory space that we'll be talking later. And some variables may impact these measurements, like such hardware or OS, compiler, the nature of the input, and so on. So let's start with time complexity. Time complexity refers to the amount of time an algorithm takes to complete a function of the size of its input. It's analyzed by counting the number of basic operations or steps that the algorithm performs in relation to its input size. It helps predict how an algorithm will scale with the input size and its OS and machine independence. Yeah, so let's see an example about this. This is just a simple sum of a list, and we also have n, there is the size of our list. We'll give a 0 to the variable s, and we have this loop that first starts with an assignment, then verification, and calculation. The assignment will only be done in the first part of this loop, and then inside the loop we have another operation, and we return s. So we can see that it's an assignment n times, and the calculation inside it will also be n times, and then return. We can make these calculations on the side, and it's something like this. We'll have a result on a function of 5n plus 3. So this 5n plus 3 might scale with n. So if we have n of 10, it goes to 53. If we have an n of 100, it will go for 503, and so on and so on. So this is why it's important to have a asymptotic complexity concept in mind, because we only want the highest order term, the one that scales. So we will drop the constant +3, and then drop the constant of coefficient at the highest order, that will be the 5. So we can say that it grows asymptotically like n. This gives an approximation complexity and ignores a lot of machine-dependent details, concentrating on the n that is a bigger picture for us. So, for example, we have a quadratic equation here, and the quadratic equation as the x squared is going to be the highest term, so we only focus on that part, and we have the logarithm equation that it's also the highest term, and we will remove the coefficient and remove the base to a default one that might be 2 or 10, depending on the mathematician that you're talking with. Why is it important to remove these coefficient and constants? If we don't remove it, we will eventually have one equation better than the other one. So it's crucial that we focus only on the highest form or highest order term, so this doesn't happen. We want to make it very simple, so our discussion and our comparison is best to be made of. While it makes it more precise, this level of detail is normally unnecessary, as I said. So we value simplicity for further and active discussion. This is not everything correct, because when we have lowest part of our functions, this will also be contradicting. But we use this calculation still because we want to actually focus on the larger number and generalizations for the discussion purposes. So some notations that we use normally, we have the big O notation, that is most important. It's the upper bound of our functions. We have the omega notation, that is going to be the lower bound, and we have the theta notation, it's the tighter bound. So we have the big O for worst case scenario, omega for the best case scenario, and theta for the average case scenario. We want big O because it's the worst case, and we always want to focus on the worst possible happening to our algorithm. If we have a function that has the O of n squared time complexity, we can say that here it has a time complexity of n squared. And we can also see that every subset that we focus on will also have its, the respective better equation during each subset. You can see right here. We have always the worst, and the average and the best can be equal or less than the worst case scenario. So we can have a function that will have a worst case scenario x squared, an average of x log x, and the best of x, or you can also have an equation that will be best, average, and worst in the same order term. Let's see an example with a sorting algorithm. This is the insertion sort. It's probably the easiest sorting algorithm that we can think of. And this is only part of the function that is most important, is just a loop. And we can see there's also a loop inside the loop. We can say that this loop will go for n minus 1 steps, because the first one will just be an attribution, not actually compared. So we can say that this is, at least this part in specific, will be O of n calls to that part. But we have another loop inside of it. This is going to be the while loop. It's going for x divided by 2 sub-rounds per round, which is a mean. We have a mean on the x divided by 2 is going to be x. So we can have x n times x calls total. We can also say in the worst case scenario that the x is going to be the next values. So we can say that this function is going to be an average of n squared, a worst case scenario also of n squared, as we have two then inside the while loop, and the best case scenario of n if we only have one sub-round per item inside our list. Comparing some sorting algorithms that are most common known, we have almost all of them have the worst case scenario as a n squared because how they are used, created on. But quick and merge are actually different. They use a technique called divide and conquer. I'm not going into detail with that because it's out of scope of this presentation, but they introduce a data structure. Before going in on space complexity, I have here something that I think it's better to show what is going on. So if we have bubble sort, for example, what is going on is it will check every item and put the highest number that it can find in the end. So when this ends, it's going to be a sorted array. It's, as you can see, it's in the worst case scenario, it's the reverted array. So it will be n squared. It's going to analyze every single one of these values. In the other hand, we have a quick sort that, by its name, it's very quick. It's going to use a divide and conquer technique. It's going to be very, very fast and log n, just to see somewhat what's going on inside our sorting algorithms. Let's see now space complexity. So in space complexity, it refers to the amount of memory or storage space required for an algorithm to solve a specific problem. It measures the number of bits or bytes required to store the data by an algorithm. This includes both input data, and any additional memory used by algorithm during the execution. To calculate this space complexity, we use two parts: the space required for the fixed part and the space required for a variable part. The fixed part includes memory instructions, constants, variables. It's independent of input size. The variable part, it's dependent on input size. So it includes recursion stack, reference variables, and much more. We will see two examples of this. We have this simple add ints. We just have A and B. We have a space for code, always. A space for simple variables. We have three, but two of them are not very important because it comes from the method that we will, the method as signature, and we don't have any defined constants, not variable parts. So we only have space complexity of 1. In this example here, it's a recursive sum, so it's the same as the before. It's summing all values on the list, but it's recursively. So we have a simple space, simple variables, and we have a space for n words. It's going to be the list, not very important because it comes from the method signature. And we have a space for recursion stack that will be n plus 1 because it's going to be the one that verifies the end of the recursion stack. So if we do this for n values, it's going to be a space complexity of n. We can see now the sorting algorithms now with space complexity average. It's almost all of them will be 1 because they don't introduce any recursion, any data structure, so it's going to be only 1. But the quick and merge, as they introduce a new data structure that will always save n values, it will be space complexity of O of n. As a final exam, I will show you this exercise. Is a very common interview exercise for FANG companies. This is given an array nums and an integer target. We want to return the two positions that, when added up, will return the target. So here we have, for example, the 2 and the 7 added up, make up the target. So we return the 0 and the 1. How can we make this? The first thing that might come to mind is the brute force solution. So we have a 4 inside of 4 that will verify if it's target, then return it. If not, return no solution found. This is going to be a time complexity of n squared because we have a for loop instead of for loop. So we just check everything. But this in space complexity will be O of 1 because we don't introduce nothing that will save n values. We only have a simple variable, multiple simple variables, not very important, so it's a O of 1. But we have another solution. It's an hash map solution. The hash map solution, it's an interesting one. It's a bit harder to understand at first, but after understanding it's easier. So we have a hash map, and we will save the value inside of it. So let's see. We have a loop. Inside the loop, we will try to match the target minus the current value. And then if that result is inside the hash map, then we will return the positions. If not, we will add the current value to the hash map. And then it will work like this. And we'll have a time complexity of n, because it's only a for loop. Nothing crazy happens here. But in the other hand, we also have a space complexity of n, because we are using an hash map to put every value inside of it, in the worst case scenario at least. And one thing important to note in hash maps is that when we do a get inside an hash map, it will be O of 1. So that's why it's very good for a lower time complexity when using an hash map. So at the end of this discussion, no, not a discussion, a talk, we know how to evaluate time and space complexity, at least I hope, understand the difference between different subsets, and why big O notation is more important, and how to calculate this big O notation, how different sorting algorithms have different evaluations, and how to apply those complexities to the real problems. And that's it by my side. Thank you very much.